Alright, so our next topic in our quantum mechanics unit is dealing with, kind of going into nuclear physics, and is dealing with the Bohr model, Niels Bohr model, and atomic transitions. Okay, so Niels Bohr was instrumental in discovering the discrete orbital nature of electrons, kind of like how they go around their atom in their orbitals, and as they orbit the nucleus of an atom. So electrons reside at specific energy levels as they orbit the nucleus. The lowest energy level is known as a ground state. This corresponds to an n value of equal to 1, and that's just the label that you put on that orbital. The ionization energy is the energy needed to completely remove an electron from the atom. So, usually the way we denote this is with a series of lines that represent the orbitals, okay? And they kind of get closer and closer together. And it depends on the atom as to how many you're going to have. It's completely dependent on the atom, whether it's hydrogen or helium or whatever. So n equal to 1, this is the ground state, lowest energy state. And each subsequent one is just n equal to 2, n equal to 3, n equal to 4, n equal to 5 in this case. Like I said, you can have different amounts depending on the atom. Okay, and each amount, each energy level has a given amount of energy associated with it in order to move that electron from one level to the other. So I'm going to just kind of put some random values, just arbitrary values over here just to show you what they look like. 0 joules or 0 electron volts goes at the top, the amount that you need to ionize, and then let's say the bottom energy level is 12 electron volts, and then 6, and then say 3.2, and you guys get the idea. Okay, and basically we'll talk a little bit more in a second about why those are negative and that sort of thing, but these basically correspond to the different energy levels. Okay, so correspond to different energy levels. Okay, so as electrons move from orbital to orbital, energy is either absorbed or released by an atom to make the transition. It takes energy to move up from the ground state. Okay, so for example, let's say we've got some energy levels here. Okay, n equal to 1. Okay. By the way, back to ionization energy. Ionization energy would be the amount to cause that electron to leave. So for example, if I had an electron here, okay, it would take more than 12 electron volts in order to get it to ionize, in order to get it to leave its atom. Okay, so these are your excited states. Ground state, excited states. So these are all your excited states. Okay, so for example, if I have an electron, okay, and let's say it's here, okay, and in order to get that electron to move up to a higher energy level, okay, this is the ground state. In order to get an electron to move up, let's say to here, okay, I have to add energy, okay, and most of the time this is in the form of a photon that bombards the atom. Okay, so I'm going to put like a little wave here. This is our little photon. Okay, so energy from the outside, photon must be absorbed. So energy has to be absorbed. And the amount of energy that contains is equal to HF. Okay, just like we've talked about before. The amount of energy that photon has. Okay, so let's say for example, this was negative 10 electron volts, as this was, I don't know, negative 8 electron volts. Okay, you would have to have a photon in order to get that electron to jump from this n equal to 2 level to n equal to 4 level. You would have to have a photon that has 2 electron volts of energy. No more, no less, because you can't go in between orbitals. Okay, so for example, if this photon had, say, 1 electron volt of energy, okay, it wouldn't make it up here, okay, and you can't reside somewhere in the middle of an orbital. Either you're on an orbital or you're not, okay? So this photon that it absorbs would have to have exactly 2 electron volts of energy in this case, okay? So when you go up, energy is absorbed. When you go down, guess what? So n equal to 1, n equal to 2, 3, energy is released. So let's say we have an electron here, and it goes down. Energy in the form of a photon is released. And guess by how much? E equals hf. So, for example, let's say this was, once again, let's do the 8 and 10. Okay. If this electron jumps from here to here, how much energy is released? Okay, well, to make that jump, that's 2 electron volts. Basically, it's always just the absolute value. It's just the difference between them. So that's 2 electron volts. So the amount of energy that this photon would possess would be equal to 2 electron volts. And you could find the frequency of that light, okay, just by plugging it into your equation, okay? So the key here is that this amount of energy is related to the frequency of light energy that is absorbed or released to make the transition. Electrons cannot move to any space between specific orbitals or energy levels, okay? If they don't have enough energy to make the move to the next level, then they can't. They can't go floating in between levels. You have to have a discrete amount, okay? All right, so let's do an example. This kind of has a bunch of our past topics, too, that we've talked about. So an experimenter determines that when a beam of monoenergetic electrons bombards a sample of pure gas, atoms of the gas are excited. If the kinetic energy of each electron in the beam is 3.7 electron volts or greater. Okay, determine the de Broglie wavelength of the 3.7 electron volt electrons. Okay, well, let's take a look. We have an equation for de Broglie wavelength. Okay, so let's see. We know how much energy has 3.7 electron volts. Okay, so what we need here, we know Planck's constant. We know the mass of an electron. You know that, 9.11 times 10 to the minus 31st kilograms. Okay, velocity. Ooh, how do we find the speed of an electron? Well, we have its energy. All right, guys, what equation relates energy and speed? You know this. Kinetic energy. Okay, let's go ahead and convert this energy to joules. Okay, so 3.7 electron volts. Remember, there's in 1 electron volt, there's 1.6 times 10 to the minus, just blank, 19th joules for every electron volt. Okay, so that's going to be equal to 5.92 times 10 to the minus 19th joules. Okay, that's the amount of energy. Okay, so let's find the velocity. That's going to be 5.92 times 10 to the minus 19th joules equals 1/2 m, that's the mass of the electron, times v squared, which is what we're solving for. Okay, and you get a velocity of, let's see, 1.14 times 10 to the 6th meters per second. So we're going to plug that in for our velocity. We know mass, we know Planck's constant, so all we have to do is solve for our de Broglie wavelength. So that's going to be equal to 6.63 times 10 to the minus 34th joules times seconds divided by our mass, 9.11 times 10 to the minus 31st kilograms times our velocity, which we just found. Okay, and once we do that, we get our de Broglie wavelength equal to 6.38 times 10 to the minus 10th. And what are our units for wavelength? It's going to be the meter. Okay. All right. So once the gas is excited by 3.7 electron volt electrons, it emits monochromatic light. Okay. So basically, you excite the gas, and then as those electrons that are in that atom go back down to their ground state, they give off photons. Okay. Okay, so you excite them. They then, after they're excited, go back down to their ground state and they emit photons. Okay, determine the wavelength of this light that's emitted. Okay, well, E equals HF. This is going to be the amount of energy that you add to the gas, which is 3.7 electron volts. Okay, but we already converted that into joules. We found that to be 5.92 times 10 to the minus 19th joules. We know Planck's constant. Frequency. We can find the frequency, and then once we know the frequency, we can find the wavelength. Okay, so let's do that. Equals 6.63 times 10 to the minus 34th joules times second. And actually, here's a little shortcut for you, if you're interested. We know that C equals frequency times lambda, right? Speed of light. And we want to find lambda. Okay, so frequency is going to be equal to C over lambda. So we can plug C over lambda into our equation for frequency. Okay, so that's going to be 3 times 10 to the 8th meters per second divided by lambda. See what I just did? Okay, I just plugged that equation in for this one. You don't have to do it that way, but that's all. I just thought I'd show you a little shortcut. And when we solve for lambda, we get 3.36 times 10 to the minus 7th meters, which is the same thing as 336 nanometers. Which on the AP exam you don't have to convert that, but sometimes it's just easier to see. All right. So experiments reveal that 2 additional wavelengths are emitted if the beam energy is raised to at least 4.9 electron volts. In the space below, construct an energy level diagram consistent with this information and determine the energies of the photons associated with these 2 additional wavelengths. Okay, so we already know, this is 0 energy at the top, that it says that 2 additional wavelengths are emitted if the beam energy is raised. So basically you add 4.9 electron volts and 2 additional wavelengths are given off. And this is how that works. This is the amount of energy that you add. Guys, that negative sign just means that that's how much energy has to be basically absorbed, okay, in order to move an electron up to its ground state, up to its ionization. So just stick it there. Don't worry about it's just semantics. Anyway, we already know that we have an energy level that's 3.7 electron volts because in the previous problem it said that we absorbed 3.7 electron volt electrons as well. Okay, so 3.7 electron volt, we had a transition there, and then it said that 2 additional wavelengths were emitted. Well, let's take a look. We can have a transition here, here, and here. Okay, see, 3 wavelengths. It says 2 additional, so that's 3 total. So if we have electrons that go from, let's say, n equal to 3, okay, then if we have an electron that moves, it can only move this discrete amount, this whole discrete amount, or this discrete amount right here. And it wants you to determine the energies of the photons for these levels. Well, we already know one of them is going to be 4.9 electron volts. This one right here, right? 0 to 4.9. Sorry. We already know one of them is going to be 3.7 from here to here. And then the only one we have left, because these are the orbitals we have, is the transition between, because you couldn't an electron go from 0 to 3.7 and then from 3.7 to 4.9, and that would be this transition right here. So it's just going to be 4.9 minus 3.7, which is 1.2 electron volts. So these are the energies associated, okay? These are the energies associated with each of those wavelength those transitions.